All right, good afternoon. Um, Thanks for attending today. My name is Buck Nye, president of HC&I Company. Um, with us today, we have Shawn Manisto, National Sales Manager for Ruppair. And Shawn is going to talk to you about integrated warehouse heating and ventilation design. Shawn, I don't know if you want to give a little bit about your background in the industry, but we really appreciate you taking the time to be with us today, and look forward to seeing your presentation.
Thanks, Buck. Again, like Buck said, my name is Shawn Manisto with Ruppair Management. A little bit about myself. I've been in the industry for the past 32 years, kind of seen many different parts of the industry, starting out as out on the floor at Rupp as an intern, from there going into engineering, into sales, and actually into sales management. So one of the areas we specialize in is the warehouse heating side of things. Rupp's been around for the past 50 plus years, with a big focus on the direct fiber products, and with that, a big part in the warehouse industry, which we're going to talk about today. So today's goals are basically look at warehouse design considerations, traditional heating methods done for warehouses, changes the status quo. What's going to be changing as we move forward in time. There's been a lot that's changed. Modern design and integration, why it's important in today's warehouse. Kind of break down, I call these big box facilities in 4 different characteristics. Warehousing, high volume product storage, distribution centers, storage and distribution of products, fulfillment centers, which is becoming gigantic now with the obviously Amazon that's out there. So receiving, processing, fulfillment of orders. These are going to be your smaller type facilities. But then also within the big box facility, I also like to talk about manufacturing, because within manufacturing, you have a lot of big open areas that you have to deal with beyond, general ventilation rates. So design considerations when looking at these big box type facilities is understanding the size. So these are all the things we're going to have to understand before we get into the design criteria, but the size of that building. With these big box type heating applications, you're dealing with buildings anywhere from 10,000 square feet to 1 million plus. I personally myself have done them up to about 2 million square feet. Ceiling heights, 24 foot to 90 foot. Commonly, if you get some of the automated racking systems, you're going to have some high bay areas that might get into that 70 to 90 foot range in height. So make sure you understand that criteria. What type of construction is going to be a precast or steel type construction? Insulation values that may exist for the construction, dock doors, the number and type. Is zoning required in this facility? In other words, is this box going to have just one tenant or could it have multiple tenants? Understanding if this is an unoccupied spec type building that they just want to make sure they want to hold for freeze protection, or understanding if it's going to be an occupied tenant building. And the biggest thing is to have systems in place that can maybe satisfy today, the spec building, but also meet the demand of tomorrow, the tenant building. Other design considerations as you start looking at the HVAC system for these warehouses is the racking layout, how the racking layout exists in that facility. Air movement and distribution, make sure we have good coverage throughout the facility. Is redundancy needed or wanted? So maybe you have a small facility that maybe one heating system or one fan could cover, but maybe you want to look at some redundancy characteristics. Uniform temperatures, how can you get uniform temperatures that cover through the entire building? Ventilation requirements, what's needed. Pressurization control, why is important. And then understand how you take all these things and develop a load or basically a heat calculation for what's required to heat these boxes. So one big thing is the ventilation requirements. It's important to point out that even an empty box does need some level of ventilation. As far as ASHRAE references in the IMC codes, they will reference a warehouse as having a minimum of 0.06 CFM per square foot. In some cases, people will take exception to that when it's an unoccupied spec building, but as you can see as we go through this presentation today, some level of ventilation is still critical for keeping these buildings dry and clean and ready for tenant finish out when that day comes. But other areas may require higher demand ventilation. Shipping areas, receiving, sorting, packaging, light assembly areas. This is additional areas that need higher level of ventilation rates. On top of that, if you have occupied facilities run LP forklifts, that can be a big impact in basically the emissions or the indoor air quality of that facility and those require up to about 5,000 CFM per forklift. Other things that we need to take account of is the battery charging areas and other processes that might be in place. However, it may be a warehouse, they may have maybe some light assembly or some other welding going on in this type of warehouse. So why is building pressurization important? Maintaining a slight positive pressure is critical to really any building, preventing infiltration, cold drafts, keeping out debris, dust, from the dock areas. Insect control is becoming a big part of this. That's why we're going to talk a lot about mechanical pressurizing these spaces. A's and distribution to perimeter surfaces, so it allows you to get air to where the air could be infiltrating into that building. Like I mentioned earlier, the indoor air quality benefits of basically mechanically controlling how that air comes into that building rather than just having it infiltrate into the building. Once we have a lot of this criteria, and we're going to talk more about this later in the presentation, but you're going to basically understand how you need to get this building envelope heated, what things are involved. So in this case here, this kind of just shows you a snapshot of the skin losses that are involved. And the big thing with the skin losses is most engineers can run this calculation and all your calcs are going to come up fairly close, plus or minus 5%. But the big part of that is going to be in basically the infiltration factor. The infiltration factor is the key to understanding these buildings, how they live and breathe. Again, what are the ventilation requirements? What are the code requirements? But more importantly, what happens when dock doors open? What happens when dock doors are facing a west wall rather than a east wall? What are the construction characteristics that may impact this infiltration rate? And what's the age of the building? The biggest thing we see now is with these new buildings, it's a very, very tight construction. So the biggest thing with that tight construction is if you're bringing heated air into the building to meet the ventilation rates, that air needs to get back out as well. So we're going to talk more about that. Just kind of some history on the gas-fired heating side of the industry. Basically, gas-fired heaters were first introduced back in the 1920s. Many of you probably know the Resner name. They kind of introduced the first unit heaters that were put out into circulation. From there was adopted in 1920 the air rotation units. The air rotation units we're going to talk more about as far as how they were used in that time. In 1925 is kind of where things began, where the American Gas Association and test labs opened up, starting to define some testing for this type of product. And up the upper right-hand corner, you can see kind of that open flame burner. This is kind of where the concept of the direct fired technology comes into play. Just that open flame. In the 1950s, kind of when direct fired units were first introduced into the industry. In the 70s is where recirculating type direct fired heaters came into the industry. We're going to explain more about those later. And then the 80s, in 1980 and in 2003 were kind of the pivot points for big changes in the governing bodies, the ANSI standards that kind of looked at how direct fired is utilized and how it can be safe. And today, the biggest thing is about integrating solutions with modern controls and monitoring, making sure that within all of this development of these standards, making sure we can control these buildings to meet the need and the requirements of the user. So gas-fired heating products can be broken down into two primary categories: direct fired, which you can see on your left-hand side, versus indirect fired systems you can see on your right-hand side. And we're going to talk about all of them. In the case of indirect fired systems, this has to do with having a heat exchanger like we see in this picture right here. In the case of an indirect fired system, we're basically going to do all the firing outside of the airstream that goes in the building and basically heat up the exchanger and do a transfer of that heated air into the space. Commonly, you're going to see the old style indirect fired units were going to be a clamshell style. Now we've got in-shot tubes, or in the case of large indirect fired air handling systems, you're going to have what's called a drum and tube, basically like a big barrel they'd fire a burner into and then run it back through some secondary bypass tubes. Traditionally, indirect fired systems are going to be anything from an on-off control to a 6-to-1 turn down on a single exchanger. Today, you'll get higher turn down capabilities off of indirect fired units by doing split burner capacities on the end shot style burners, or maybe going to multiple heat exchangers within a package. Typically, non-condensating furnaces are efficient at about 80% efficient. Anytime you get above 80% efficient, you're gonna start getting into a condensating type furnace. So the first category of the, and again, we're going to touch on basically 3 indirect fired common uses for heating these warehouses. And the first is going to be unit heaters. Unit heaters are basically, the most common unit heater is going to be a gas fired. They do have electric and steam as well, but gas fired we're going to talk about today. Unit heaters are typically hung, typically operated by a small prop fan in the back or a direct drive or some type of a driven blower. These utilize 100% return air. No outside air is introduced. Normally a lower temperature rise because they're utilizing that return air. And commonly they're going to be staged heating. They may have some modulation, but most commonly they're going to be just staged heat control. The benefits of unit heaters, it doesn't take up any floor space, and it does provide some redundancy and some zone heating capabilities. So a lot of times it's good for a small space for some zone heating capabilities. The biggest drawbacks is no outside air introduction. So typically, like I'm actually based in Minnesota here. Minnesota does a lot of unit heaters for some of their speculative type buildings, but they're always going to be accommodated by a makeup air system that's going to be utilized to bring that fresh air into the space. So in this case, in Minnesota, we're starting to convert a lot more units over to just straight up recirculating style direct fired makeup air systems. No pressure control or infiltration control, can create stratification in hot spots because again, they're designed just to be the heat source. The indirect fired inefficiencies and really no summer ventilation. So this is kind of just a heat only winter application product. Next, we get into the air rotation type system. The air rotation type system is another indirect fired heat source. Typically, these are 100% inside air or recirculating air. This image over here just kind of shows you an image of what they would look like, basically having 100% return air coming into the system, getting heated up, and then getting discharged across the building here. Some do have the ability to bring in some level of fresh air, but typically they are not. Indoor floor mounted, continuous blower operation, and heating, to meet heating needs. The biggest benefit on air rotation systems is very few units. But in continuous air movement. So the biggest thing is that this is a dated product now from the standpoint of having HVLS fans available. We're going to talk more about those later. The biggest drawbacks is floor space that these occupy. They take up a lot of floor space, which now in these warehouses, the floor is basically the value. High upfront costs, very high upfront costs. Typically no outside air, no pressure control, no redundancy. That's the biggest thing, is because you can get by with maybe one unit to cover a big area. There's no redundancy. If this unit goes down, it goes down. And obviously the indirect fired efficiencies. The last indirect fired source is going to be radiant tube heat. Radiant tube heat is basically radiant heat off on surfaces. Basically, it's going to radiate a temperature or a radiant temperature across onto a surface. It does not do any direct heating of the air, but instead it basically heats surfaces. Commonly mounted in dock door areas. One thing I'll say about radiant tube heat, this is a very good means of, if you have a moderate, if you're trying to hold a moderate temperature in a warehouse, maybe down to 50 degrees, but you want to have some spot heating where you have workers or dock areas, this is a big benefit product. Typically installed about 15 to 30 foot above floor level. The big benefits on radiant tube heat are having some of that zone heating capability, and they are good in redundancy because you're going to have several of them to cover a big type facility. Obviously, the drawbacks here is we're not bringing any air in, is going to have no indoor air quality benefits from the standpoint of bringing in fresh air. Again, no pressurization control or infiltration control. And it's going to create, in some cases, stratification, also stagnant air. So if ventilation is not part of the equation, stagnant air can be a challenge here. And then higher ceilings are sometimes make this product not available. So the biggest thing between indirect fired as we transition in direct fired is looking at the simplicity of direct fired. Over to the right, you just kind of see just a general snapshot of potential cost savings utilizing direct fired products. We're going to talk more about that. But the big thing, the big move towards direct fired is going to be looking at the ability to save money, have a simpler product, have a safe product, and have a sustainable product. Again, looking at the campfire flame down below where we started out with that open flame, the concept the same way, just put into a safe means of heating these buildings. This is just a cross-sectional area of what a direct fired flame looks like. So unlike the indirect fired units where you're going to have a heat exchanger that you're going to be heating the air in and having a flue that dumps basically the flue gases out into the atmosphere, in this case here, the combustion is going to exist within the fresh air stream. So as the fresh air comes from outside, it goes across this open flame burner, and basically all the heat is utilized into the building. No flues or vents needed on this product. This here is going to show you just a nice illustration of how a direct fired unit can modulate. Again, the big benefit of a direct fired system over indirect fire is having a high turn down ratio. Most direct fired units will have a 30-to-1 turn down ratio type burner. Now, one thing to understand is that even though a burner can have a 30-to-1 turn down ratio, typically in a true application, you're going to come across about a 20-to-1 turn down ratio when properly applied on a direct fired unit. So you can kind of see this burner modulating from high fire down to low fire. The other big benefit over indirect fired systems is having that 100% thermal efficiency. We're going to be about 92% sensible heating capability with 8% being latent gain. The idea behind direct fired as well is an overall reduction of greenhouse emissions. Because you're utilizing all that heat to heat the space, you can get by with firing at lower BTUs rather than having an indirect fire that you're going to be putting some of those BTUs out into the atmosphere. The really only holdback on direct fired systems is the one restriction, according to the International Fuel Code, is that it is not permitted in sleeping quarters. You will come across in some cases where school districts may restrict it, but this is really the only place that it cannot be used based on code. A question in the past is direct fired safe? And I think this has kind of been put to bed, but basically direct fired units are very safe. They are all, when you come to the non-recirculating style systems, they're tested to ANSI Z 3.4. If it is a recirculated style systems, they're tested to ANSI Z 3.18. Just a few things within direct fired units is there's a lot of redundancy and safeties in play. Basically start interlocks. If you have VFDs, those have to be interlocked before a burner can light. End switches and dampers, airflow switches, high temp limits, flame safety relays. Some other things not shown here are gas pressure switches, high and low. So a lot of redundancy on the direct fired systems for safety. Within the direct fired units, we're going to kind of talk about two different primary types of direct fired units: 100% outside air direct fired units, and later we'll talk about recirculating style direct fired units. In the case of 100% outside air direct fired units, commonly known as makeup airs, MUAs or MAUs, some people refer to them as, these are designed for replacing 100% outside air into a building that's been exhausted for some reason. Discharge temperatures on these products will range anywhere from 70 to 160. Again, 100% outside air into the building. These are bringing in. And commonly they can have VFDs to allow some level of variable air volume control. So if you have a unit that's designed for 10,000 CFM with a VFD, you could have some variable control and may vary that down to as low as 5,000 CFM. So commonly 100% direct fired makeup air units are seen where areas of exhaust exist. In the case of this warehouse we're talking about today, it could be maybe they put a welding bay in this area, or they have a paint booth system. These are common areas where anytime we exhaust out air, we need to bring air back into the building. So 100% outside air is used for direct fired heating is done. The biggest thing to know about from the control side is that when 100% outside air direct fired units are used for space heating, that they will have some cycling characteristics to them. Either they'll have to cycle on and off, almost like a unit heater, or they'll have to be continually operating and modulate the burner, but continually bring in outside air. So the challenges with the cycling system is obviously having that staged air control, having intermittent air movement, it's inconsistent building pressurization. So as a unit goes on and off, you're going to have that basically that inconsistent building pressurization. no compliancy to meeting the ASHRAE ventilation codes when these systems are off, and that can also create stratification. In the case of having it continually operated in the occupied mode, the biggest challenges there is having high expenses. Always introducing that 100% outside air to the space that may not be needed. Maybe it's beyond the ventilation code requirements. Overpressurizing the space and making sure in this case here that you do have a system that was designed to do a full modulation type system. Preferably if it's going to be 100%, having not only modulating heat control, but also modulating blower control. So you can compensate for overpressurization and meeting minimum code requirements, not bringing too much air. One common misconception is also about a draw through a push through style system. This illustration just kind of gives you a snapshot of two different ways of the 100% high temp units that are used for these heating warehouses, between a push through style system and a draw through. And the biggest thing to point out is that although CFMs may appear to be different, in the end, they're going to utilize the same amount of CFM to create the BTU capacity to heat this building. So kind of a roundup on the 100% outside air direct fired heaters. Big benefits: upfront costs and operating expenses on direct fired units overall is a big benefit. Does not use floor space because it has the ability to be hung or up on a roof. And now, because we have 100% outside air, we have the summer ventilation benefits. Some of the drawbacks, like I said, when the unit is utilized as a cycling style system, you may have stratification or hot spots. Inconsistent building pressurization we've talked about, not being compliant to that ASHRAE 62.1 or the IMC codes. And operating can be expensive when basically the space temperature is satisfied, meaning we're going to overheat or overpressurize the space if that VFD is not in play. Now we're going to kind of transition into the direct fired recirc approach. And there's various approaches when we talk about recirc. The next slide is going to kind of break this down a little bit further, but various approaches: 80-20 versus 60-40 versus 50-50. And if you don't know what that means, I'll explain it here in a second. But the big thing with direct fired recirc units is having good flexibility for installation, good pressure control, and air and heat modulation standard across the line on this product. So the basically recirculating approaches: 80-20, 50-50, 60-40. What does this all mean? So the 80-20, what that's really referring to, you guys may have seen that terminology in the industry in the past, but the 80% refers to the maximum amount of return air that can be brought through the system. So over to the right-hand side here, we see an illustration of a return air system. And what this is basically this burner area we're looking at here in the center. This is designed for consistent 20% outside air. The balance of the air is either going to come through a fresh air bypass damper above to bring in 80% here, or a return damper coming back from the building 80% through here. So traditional 80-20 units or traditional recirc style systems were referred to as 80-20 units for this reason: 20% constant fresh air and the 80% balance coming in through the top chamber or the bottom chamber. Commonly used in the past, these are more common for balancing or pressurization of building rather than just straight up heating of buildings. But that's kind of where the 80-20 came from. Next, I'm going to talk about 50-50 systems. 50-50 is a term that got picked up as more of a fixed recirc style system. In this case here, typically most manufacturers, what they're going to do is they're still going to have their burner chamber here designed for 20%, but they're going to basically fix a minimum of 30% additional across the fresh air and the balance of the 50% through the return air here. But in the 50-50 system, most commonly, those are going to be more like the 100% outside air heating systems that are going to be on-off style systems, but have basically a fixed recirc position in a 50% outside, 50% return mode application. Then we get into what we refer to as a 60-40 system. Oops, sorry. 60-40 system, I like to call that the hybrid style system. And why it's the hybrid style system is it's basically kind of a combination of the 80/20 style system along with a smaller version. The reason the hybrid style system was made really is to have just a smaller footprint piece of equipment along with continual building pressure control. We'll talk about that more here in a second. This kind of puts the illustrations kind of side by side. This design building here is going to be 160,000 square feet. Starting out at -5 degrees, want to maintain 65 degrees. So we've already ran this through our heat calculations and know what we have for a heat load. Traditionally, in the old A20 tile systems, we need to have two 28,500 CFM units. We're going to talk a little in a second here also about the ANSI requirements for heating. Because these are going to be limited to a lower temperature rise capability. The 60/40 style systems can utilize two 13-250 units, where the 50/50 will be the smallest units. But again, these are going to be more of a cycling on-off system. They have the highest temperature capability of the recirc style systems. Down here is the chart that I was just referring to as far as the capability of temperature rise. What this number across the top here equates to is the amount of outside air, 20% outside air, 40% outside air, 50% outside air. And basically what the ANSI standards did back in 2002 is basically, or 2003, looked at how much fresh air do we need to introduce to a space with a direct fluid unit to have safe combustion, safe emissions into the space. And that's basically what this did. So at 20% outside air, we're limited to 49-degree temperature rise. At a 40, we're limited to 98, 50, 122. And you can see the more fresh air you bring in, the more temperature rise capability you'll have. So again, the 60/40 hybrid came from two things. Make sure we have a small piece of equipment at the lowest cost possible, but meet the best operating savings. So taking some of that 80/20 traditional concept and putting it into a smaller footprint, but then also along with that, making sure that we have, the amount of fresh air needed to meet the emission levels for the ANSI standard and provide just a clean, safe heating product for the industry. Within the flexibility side with the recirc style systems, there's a lot of means to install this product. Everything from roof style mount to hung to vertical indoor, like the traditional air rotation style system. Then to an outdoor style system as well. So a lot of flexibility as far as how you can install this piece of equipment. Direct fire controls. When you get to the temperature controls, you're going to have occupied and unoccupied capabilities. And the most important thing within these recirc style units is make sure you have controls that can give you this control and this flexibility. Occupied mode, basically continually operating to meet those ventilation requirements. Unoccupied can be energized on call for heat only. But then also third, having the ability to have this equipment operate in that summertime ventilation mode of 100% outside air. So a lot of flexibility from continuous heating mode to cycled unoccupied mode to high volumes of fresh air for summer mode. Within this, make sure you have pressure controls that control the space pressure continuously, and making sure you incorporate things like smoke detectors, make sure that's interfaced to the products as well, to be able to shut down a system in case of a fire. So the big benefits on the recirc style systems is the lowest operating cost overall for the direct fluid units. We talked about the 5 different systems. We talked about the unit heaters. We talked about air rotation. We talked about the radiant tube heat. Next, we talked about the 100%, and now we're talking about the recircs. So again, all of them kind of have their place, but this is kind of where we see the biggest bang for the buck. So that consistently meeting those ASHRAE standards, meaning the pressure control. If you're maintaining pressure in the space, you're going to mechanically control that infiltration. Continuous air movement to help eliminate destratification the best you can. Having those summer capabilities for ventilation we talked about. The biggest drawbacks to these units could be the zone heating versus the amount of unit heaters versus radiant tube heats. So in the case of a small building, you may get by with just one direct fire system, but you do lose some of the capability of some of the redundancy characteristics of that product. So the heating system results when you pick the right products is meeting all the heating needs, from skin losses to infiltration to building loads. So you see there's a lot of repetition here when we talk about the infiltration side and the pressure control. Eliminates infiltration and draft, ventilation, meeting the ventilation requirements needed, and positive pressurization. That's kind of your end result of the best product selection. So earlier on, we talked about those design considerations. One of the design considerations was understanding if it's going to be an unoccupied spec building or if it's going to be an occupied tenant building. So the biggest thing is when we're working on these unoccupied spec buildings, the biggest thing may be the mechanicals or the generals or the developers of this time are mostly concerned about lowest cost. Lowest cost are what gets them to basically when a tenant's going to occupy. Ventilation rate, maybe a false perception may not be needed. Like I said, you're going to find out it is needed to some level. So a lot of times they're just going to put a heat source in there and not worry about ventilation rates. But once occupied, the biggest thing to remember when you're doing a speculative type building is to think forward, because a lot of times some minimal costs paid today will have big benefits tomorrow. Working in some of the bells and whistles that are going to really be needed for that tenant when they occupy the space. Like I said, here in Minnesota, a lot of shell buildings get built out of just unit heaters, and the moment a tenant moves in, they're doing a lot of tenant finish out. So building the flexibility, think different based on what new technologies are out there, what products allow you some flexibility. Consider the controlled ventilation. Controlling ventilation is overall is a big savings. So as we talked about this, common industrial challenges. So within the warehouse industry, the biggest thing you're going to see, especially in these speculative tile buildings, is moisture control. Moisture issues that may exist in the building. Non-integrated solutions. We have multiple manufacturers providing different products to the space or products to the warehouse that may not interface with each other. One exhaust fan may not talk to a heater may not talk to a damper that's opening and closing elsewhere in the building. So having that integration. Understanding four-season comfort. There's more than just winter we're talking about here. We're talking about spring, summer, and fall. Legacy products. What do legacy products bring? Sometimes they may bring a low cost up front, but they may bring some challenges. Out of date, inefficient, inflexible controls, and expensive BMF systems for monitoring down the road. So one big challenge we see specifically in these speculative style buildings is moisture issues. This is just some snapshots of a project. I think this project was in Chicago, if I remember right. But just why lack of ventilation and air movement in that spec phase is so critical. We've seen this multiple times where now you're into mold remediation. You're basically paying an expense that did not have to be paid in the past. So you can see the mold in the corners. Any place you have a conductive surface, you're hitting that dew point level, you're basically conducting and creating mold. So that's one reason why system integration is so important. This illustration just kind of shows this is about 300,000 square foot warehouse integrating all the products that should be used in a system in a warehouse application. Now I'll go through these kind of one by one. So most importantly is, if nothing else, is beyond just having those heaters on the building is having gravity vents in place. Again, air in is air out. So if you're utilizing basically the direct fired systems, either 100% or recirculating style, basically air in, which is called out by code, needs to have air out. Again, these buildings have gotten so tight that, just having doors alone in the space with cracks around them is not enough normally to relieve these buildings. So gravity vents is a critical part of the design to make sure you meet those ventilation requirements that ASHRAE is calling out for. I've been in buildings where if they don't have gravity vents and they start to have moisture issues in the building, just crack some dock doors and the moisture goes away. Probably the better solution then is to go to having prop fans or exhaust fans in place. Exhaust fans that you see here on the right-hand side, having those in place is a much better way to approach it. Lower summer air change rates with logic controls. So one thing, obviously, many have come across in the past is about having high ventilation rates in summertime, 2 air change rates, 3 air change rates, kind of some common practices within the industry. Well, one thing I'm going to show you today is how you can get by with strategically controlling your infiltration or controlling your summer ventilation rates with smaller fans, maybe less air changes, a half air change, 3/4 air change, and run them more strategically. Make sure if you're utilizing these exhaust fans and even the makeup airs that you're utilizing the newest technology. Direct drive technology is a big part of what we see every day now. So have these in place, everything on the smaller side, and make sure you have ECM motors in place. Remote adjustment and full monitoring for these fan products. So big benefits on the direct drive fans. This actually is one of our fans we build. It's actually a Prop 5 direct drive, but we actually have pre-mounted VFDs, pre-mounted disconnects. It's basically a single point power source. And actually for these products here, all they run is 3-phase power to the disconnect, and then they run a Cat 5 up to the unit for interfacing with this fan. So in this case here, we kind of went from where we had the gravity vents only in the back, but now we have the exhaust fans. So with the exhaust fans here, we have the makeup airs, which I call the front of the house typically. These are all of our dock doors exist. And we have the exhaust fans in the back. And basically we're going to introduce air and pressurize the space and introduce air back to the exhaust fans in the back corner. Something to be aware of as well when you're doing your design layouts is where your north and west walls lay as well. They're normally the most common areas for condensation and buildup. So making sure you have good air movement across those north and west walls. Next, we get into the HVLS fans, what benefits they can provide to these applications. Very economical for moving a lot of air. Like I said, the air rotation, indirect air rotations were big in the past because they kind of did that. They, not only brought in heat, but they were able to turn over large amounts of air within the space. Now with the innovation of HVLS, they've kind of taken that place. Up to 300,000 CFM at 17 cents an hour is very, very economical. Great for destratification in the wintertime, but also great for summertime cooling, having some of that sensible cooling across your body. Prevents basically summer slab sweating, but also helps prevent winter dew point on those cold surfaces. This kind of a picture of showing, we can see in these high areas here, this is basically the stratification within a space with the HVLS fans off. And if we go to the next slide here, it just kind of pins down kind of where we were running in much more balanced temperature ranges, a 1 degree temperature range with the HVLS fans and on when we're in a heating mode application. This illustration here gives you a good picture of what would happen during a summer cooling mode, having that cold air, having that air getting pushed down from the floor. And then this is more of a thermodynamics picture in a winter heat application in a forward driven mode. You can see the heat as it's pushing the heated plume down towards the floor. And how we start to create uniformity within the space as it continues to run. And then also another thermodynamic slide on basically the fans operating in a reverse rotation. Both have their place based on the layout of the building. You see as we start neutralizing and getting more uniform temperatures throughout the building here. So back to the integration slide on the HVLS, we basically commonly put the HVLS where you're going to have occupancy, dock areas where a lot of people are going to be working. If there was an assembly area back in here, we may put 4 HVLS back in this area, but then also having them interface to an overall control system that can control all the fans independently or as a zone system. So the next part of the equation to solve some of these problems is having those modern controls. Modern controls that are designed to incorporate with the heating system in the overall warehouse ventilation system, rather than having some third-party controls. The biggest benefit is integration of the whole building as one, not just someone controlling exhaust fans here, heaters there, HVLS there. having that integrated as one. Improve safety, quality, and serviceability. When it's underneath one platform, it's easy to service and understand. Set up as an application, set application specific. The nice thing about these integrated controls is that they can be set for the specific application. If it happens to be the logistics center, or if it happens to be a manufacturing facility, they may have different purposes in what they're trying to do. Have the ability to do remote software updates for these things, reduce components, have one board replace a bunch of components, and then also compatible to make sure that within this, it could tie into a third-party BMS if needed. Other things we've incorporated into the modern heaters today is moving away from things like mechanical photohelix into pressure transducers. VFDs are kind of a standard across the board on all products, making sure you have that flexibility, like I said, not only of burner modulation, but also of fan modulation. This is just an image of one of our rough direct fired heaters, kind of doing the walk up here. This is our main control board. This is one of our touchscreen pads that our technicians use when they do setup and commissioning of the equipment. Just another little image of kind of how things have been cleaned up and compact, no more of the old. So one thing about our industry is our industry was basically very slow to adopt. You're still seeing a lot of manufacturers using some of those 1970, 1960 type components. This is kind of just bringing it to today's technology. Having easy to use remote interfaces for the operators. Simple Cat5 connections, very simple to install, no longer having to run 15 wires from a makeup air system down to a control panel, but rather just have a single Cat5. Having everything from not only temperature control, but also humidity control. Having the ability to pick up on all alerts on what's going on with that equipment. Out on a flame failure, not providing an airflow switch, what's going on. And simple things like having password protection on locking out settings. Simple navigation from user settings, factory settings, service settings. And like I said, having not only controls on the heating style system, but also carrying them across into the exhaust fans and the HVLS. This is just some images of one of our control packages we have for our exhaust fans and HVLS. Having that zoning capability, be able to control different zones within a building is pretty common now. Especially if you have multiple purposes in these areas. Have the ability to set schedules, monitor temperatures, manual modes are available. So within the controls, also having some nice capabilities to control things beyond just the winter heating, but also we've incorporated what's called a winter dry mode. What a winter dry mode can be utilized is most commonly in these spec style buildings. We have a lot of post-construction moisture that may exist from everything drying. Having the ability to look at dew points within a space to dew points of outside, and knowing when it's logical to bring in more outside air for ventilating the system. Beyond the winter dry mode capability, also having a system in place that can also be a summer vent mode, basically recognizing kind of the same conditions, but we have an activation point here where we look at space temperature, where we're too warm in the space. We can start activating different configurations saying, right now, today, this summer day is a dry, cool day. We want to utilize this for some free economizer cooling and automatically introducing that into the space as needed. So increasing ventilation rates when the best time of day stands. So between the summer vent mode and back here to the winter dry mode is where we can look at how we utilize makeup air and exhaust in an application utilizing less air change rates. Maybe it's a quarter air change, a half air change versus that 2 air change rates we talked about. But strategically ventilating these spaces when it's the best time to do it. Beyond having those mechanical economizer cooling benefits, there might also be means of having additional cooling in these spaces at times. So obviously the biggest thing about cooled spaces in the summertime is having those productivity, quality, and turnover benefits. This is just kind of some illustrations about, trying to hold temperatures below 80 degrees and how efficiencies can improve for your workers. Summer ventilation, beyond this mechanical, we get into having the option of utilizing dedicated outside air systems. Dedicated air systems we commonly use in some of the smaller applications or in spot areas of these buildings, where we'll actually put in, packaged DOAS units to meet the requirements. Again, within these DOAS units, we're meeting all those ASHRAE requirements. We're providing the pressurization, continuous air movement. Not only are they having the cooling benefits, but you can also have the heating benefits as well. These would be an indirect fired heat source at this time. Fully modulating and inverter scroll compressors technology on this product line. So control integration, the biggest thing within this integrated system is having something on the front end to look at all this, not within the building, but outside the building, being able to integrate all these controls together. So this kind of just shows the illustration of bringing everything to the next stage. We are controlling all these products, but now we're basically taking the information, putting it out to a cloud. On that cloud is we're going to have the remote monitoring and then a remote control for this system. Cloud monitoring, all of our equipment is going to have cellular technology on these, no hardwire needed to break through firewalls. You're going to basically have cellular technology, Verizon wireless on all the equipment. Have 24/7 remote monitoring, ease of maintenance, and fast diagnostics if problems exist. So no third-party BMS would be required. Within the monitoring, you're going to get everything from outside air temperature and humidity, space temperature and humidity, return temperatures, building pressure, amperages off the equipment, damper positions, how they sit, gas monitoring, if exhaust fans are on or off, and also the benefit of meeting LEED and green globe fresh air requirements. So we'll have alerts on there if you're not moving the fresh air requirements needed to meet those requirements, having LEED or green globe, and a lot more. Some views of what you'll see from this cloud service, a simple dashboard look at what equipment may be doing, temperatures within the space, humidity that may be in the space, if the unit's in a heating mode red, or if it's in a cooling mode blue, or if it's in idle mode white. Having the ability to monitor these spaces from, again, temperatures through pressure control. And you can see that we utilize this a lot in our diagnosis and troubleshooting. We can actually set up alerts. Basically, if we see patterns, we're going to basically have alerts go off that maybe show us that there's going to be a trend of something happening. If we're going to have we have a component that may be failing in the system. And then having easy control. So basically, it's just a snapshot of one of our control screens. All you can basically do, change your intake temperature activation point, change your space set point. You can change your maximum min and max discharge set points, set a scheduling within the system. And on top of that, having also the ability to have this on your phone, having an application in place to be able to do all this within your hand, to access places and spaces within the product, to be able to monitor, control settings, and set yourself alerts on what's going on in the space. So kind of a wrap up. As far as warehouse heat sizing, this is just shows one of our tools we utilize for how we size warehouse. All the criteria we talked about early, from the size of the building, the dock doors that are in the building, R values that exist. We give us some suggested infiltration values, and then you can actually adjust that to run what you need. Basically, other losses that exist based on ASHRAE codes. What you want to have for a outside temperature and indoor temperature. The software also going to give you suggestions based on what ASHRAE is going to state, because up on top we aren't showing this, but you basically can set your city and state. From there, it's going to give you design criteria you recommend. Now, what you're going to see on the left-hand side here is this doesn't quite match what we have on the right. In this case here, this client actually wanted to have 3 units rather than 2, because they wanted to have 3 zones of operation in this building. From there, basically the calculator is going to give you everything from, what the heat is needed to heat the space and what our equipment we've selected is going to offer to heat the space. So again, 4 million to heat it, we're about 4.1, a little bit extra heat available to them. Like I said, this down here, this kind of your summary of what equipment we needed. 3 heating units at 14,000 CFM, 90-degree temperature rise. In this case here, this is the spec that basically the client was looking for, basically a 0.25 air change rate along with a 20% fill factor. This is actually a client we do a lot of work with that recognizes the benefits of having ventilation both in a spec building and in an occupied building. So here's again that illustration with just the heaters laid out in this building. This is a little different box than what we saw earlier in the presentation, but just showing the heat blanketing across the doors and throwing heat to the back of the house, I call it. Oops. And from there, we have the ability to incorporate the gravity vents, which is at least better than nothing, but more importantly, having the ability to bring in exhaust fans in play. In this case here, when we put the exhaust fans in play on this design, we're actually going to be controlling the exhaust fans with the makeup air, have the ability to do both a low speed operation during general heating and then a high speed during that dry or that summer vent mode. Incorporating HVLS fans across the front of the house where that working area is going to be, and then tying this all together. Tying this all together and have this available on that cloud service. So again, this building here is a 3-zone operation, 1, 2, and 3. That's why we have it laid out in this fashion. So you can do demising walls in between these if they'd like to, and they'll be all set to run these zones all independently. So that's kind of a wrap up. I hope this give you kind of some insight on kind of the warehouse heating technology, kind of where it came from, where it's going, and you know, some of the new innovation that should be put into place moving forward. Jim, any questions?
Yep. Okay, Shawn. Yep. Thank you. There are some questions. I'll give a minute just for people to type in. Just some final kind of housekeeping stuff is that we will issue a final summary of this presentation. We'll have a link for the recording. We'll summarize the question and answers. We'll also resend the PDF file of the slide deck. And then as a reminder, 2 other things, we can issue PDH credits. Just email myself or Gina O'Donnell if you haven't done that. And then lastly, we're having our next webinar. It'll be on Tuesday, January 26th. It'll be regarding rooftop units, applied rooftop units and updates with the technologies that have been recently introduced. All right. So Shawn, let's
check your date on that, Jim.
With June 26th, did I say?
You said January.
Okay. Jay, I got the J part. Okay. So there was a question or also a statement. It might have been answered. It came up early in the presentation. It might have been covered later on, but it's we've experienced hot air accumulated below the ceiling of warehouses due to the supply diffusers being located at the bottom of the ductwork, and they're blowing downward with the returns at floor elevations. Is there a better way to reduce this hot air stagnation, this stratification?
So not having some of the, kind of the visualization of the exact application they are in, but having, number one, having return air capability will catch that a lot of heated at the top deck. Having those exhaust fans or barometric pressure in place elsewhere in the building will help move that heat across the building. So returns, having the exhaust in place. And then third would be the implementation of HVLS.
Okay, the large fans to help push the air down.
Correct.
Correct. Okay. Next is, with decarbonization and electrification becoming more prevalent in today's design considerations, what options are available to eliminate natural gas heating?
Right now, we still see the direct fired as the most efficient way of providing the heat needed to these spaces, along with meeting the ventilation requirements. If anything, the direct fired units produce, again, a smaller carbon footprint comparatively to the indirect fired systems. With that said, we are doing out west some more of the indirect fired style systems, and just doing a better way of controlling the amount of outside air coming into the building to be as efficiently and as effective as possible. And again, those are a little warmer climate regions too, not the cold climate regions like you'd have in your area.
Okay, thank you. Can energy recovery be incorporated into the unit?
In the case of our DOAS units, energy recovery can be incorporated. In the case of the the research style systems, it cannot. Now, the one thing I'll add to that as well is that, again, the amount of outside air we're exhausting, the idea behind these systems too is to, and even you can see in the illustration here, is strategically exhaust away for where the heating systems are. So for that reason, we typically don't want to incorporate the energy recovery within the box here. We want to have those exhaust points, again, those controlled amount of exhaust points away from the heating system to be able to wash the space.
Okay. Next question is sort of a mouthful. For the ANSI chart shown for the carbon monoxide based on percentage of outside air, does this assume quotes clean outside air? For these warehouses, there may be adjacent warehouses, or the rooftop HVAC units may be adjacent to the loading dock area where byproducts of exhaust are present from trucks/vehicles. I assume that consideration needs to be given to these factors, just like infiltration through loading dock doors with prevailing wind direction.
It absolutely does. I mean, basically the question states in the fact that, this is considering you have good, clean, fresh air. So within, design of these makeup air, these fresh air introduction systems, making sure you are away from exhaust points within the building, making sure that you are not near vehicle emissions. So yes, that's a fair statement to say.
Okay, the next one is most warehouses are heating and ventilating. How can you best prepare for a space that might require air conditioning in the future with minimum impact to your initial equipment selection?
So the one thing if they know that air conditioning is going to be in place, having DOAS systems or rooftop systems strategically designed and placed in the building is going to be the thing to think about. One thing is we do a lot of conditioned spaces where they still utilize the direct fired systems in the wintertime, however, because it's a much more energy efficient approach to heating these boxes. And the other thing I would suggest is this is where the HVLS fans can play a big dividend. Having the ability to have that air movement lets you get by with having, as much cooling load to that space.
Right. Another suggestion might be, some type of, air handling system where you have a empty plenum section where you can install a future chill water or DX coil. The DX coil would obviously then require a remote condensing unit.
Correct.
Okay, next is how well do your controls play with others? What they're asking about is integration with other vendors, maybe via BACnet.
That is fully capable of that. So within our cloud server, all of our units have a standalone gateway that they're controlled within our cloud service. But within that, you can also interface a third party to see all the points. So all the points that we have internally, all those points are viewable. So everything from the temperatures to humidity to positions of damper to the alerts, all those points are visible.
Okay, next, another controls question is, can the wireless communication be disabled on your controllers?
Yes, it can. If that's the choice. The benefit of having connected is obviously having the remote monitoring capability, mirroring what they're doing out in the field, having for future remote updates. But if it has to do with privacy rights or things like that, it can be disconnected. Yes.
Okay. Next two questions have to do with the spreadsheet, the calculator that you've shown towards the end of the presentation. They're asking if that is available.
We can make something we can talk about, Jim. We can make that available through HCNI. Yes.
Okay, great. And then, yeah, there it is. And then it's next is, what is the contaminant level from direct fired versus indirect fired?
I mean, within the direct fired units, and I'll try to go back to the slide here, it has the emissions. I mean, indirect fired systems are not going to produce any contaminants to the space. Where direct fired units, again, because it's an open flame burner that's producing the emissions, you're basically going to have these added emissions into the space. We actually have some additional safety bulletins. I can get into this a little more explicitly, but this is kind of the general production levels. We're typically about 50% of the value you're seeing here. So we're normally doing about 2 to 2.5 parts per million of carbon monoxide, about 2,000 carbon dioxide. So we're well below those levels that even ANSI tests for.
Okay, next one's a comment that I screwed up not only with January versus June, but the next webinar is Tuesday, June 7th. Some people have already signed up for that. We will also be resending invitations for that. All right, next question. Are there any issues with direct fired heating and condensation in docked truck interiors? If so, can you recommend some preventative strategies?
Dock truck interiors. I'm sure.
I assume you have a truck that's connected, to the dock, and the majority of the cab, not the cab, the trail of the truck is exposed to the outside.
The answer to the question is, when you have some low ventilation in place with these, you do not. So you guys are looking at the dew point levels that are within these buildings. Holding those dew points relatively low, something below 40, you're not going to see that to be an issue. But in the case of these buildings that have minimal to no ventilation, you could start getting to higher dew points where you could start get frosting in those dock areas, or when the trucks back up, you could see some frosting or moisture build up over time. Yes. And the direct fired, and let me just clarify, the direct fired units add minimal amount of moisture to the space. It's kind of also been a misnomenclature as far as direct fired units creating a lot of moisture to the space. Obviously, part of its combustion is H2O or water. But again, they actually work as a humidification system of anything else in the cold of winter, providing some level of humidification to the space.
Okay, last question. Does RUP recommend high temperature air supply at 140 degrees Fahrenheit or above? It doesn't make sense to me. The air is hot enough to burn people/products. Hot air rises in these spaces, and they can be 40 feet high. In addition, you have to coordinate the high temperature supplies of 160 degrees with the fire alarm/sprinkler system that has a standard trip setting at 165 degrees.
I'm glad that question was brought up, because I should have actually had it in the presentation. Our belief is having lower discharge temperatures. We have some competition that design their systems based off of high temperature discharges. 160 is actually based on the standard. But when we talked about the traditional 80-20 units, the air rotation style units, back in the day, that's kind of how they were, is low temperature rise, discharging 90 degrees, 100 degrees at best, and trying to move a lot more air through the space to heat it. That hybrid style system I talked about, the 60-40, traditionally we want to limit that at 120 degree discharge. The idea behind that is, again, to limit stratification and not have the problems that the question is addressing. But again, 120, typically you're modulating 120 down to 80 degrees to basically maintain that space temperature that's needed.
Okay, I think that's the last question. There were some questions about if we should sing for Buck's birthday, but the answer has been no. So let's just stay on for another minute or so. If any other questions, type in. You can also email them to myself or your HC&I salesperson afterwards if something pops into your head. We do have a survey that we ask that you could, sorry, another question. Happy birthday, Buck, sorry. Just we do have a survey to fill out. If you can do that, helps us out if we're effective with these presentations. Any questions, any applications that you have coming up, and then we also ask if there's any other topics that would be of interest of you. So that survey is very helpful for us.
And also from Rup's perspective, you know, anyone out there that you have any additional design questions, or even just want to have us do a design review, we're happy to, you know, walk through any specific application you have and give you our recommendations. My experience within the warehouse heat side is about 25 years. And the biggest thing is just the improved innovation we've seen specifically over the last 5 years, and just better ways to approach these boxes for not only the the mechanical, the engineer, the general, but more importantly, the developers and the people that actually occupy and use that space.
Okay, great.
Well, Shawn, thank you very much for taking the time to be with us today. You did a great job with your presentation.
Yeah.
You know, we look forward to supporting everyone who might need assistance with this. And, you know, if you have any questions, we have in-house expert Jeremy White. He can get you started. He'll work with whoever your particular salesperson might be. Jeremy is extremely well versed in the warehouse design process, and you know, works very closely with Shawn. So again, Shawn, thank you very much, and everybody, we appreciate you attending today, and we will see you all next time.